All right, so in chapter 4, we're going to start looking at some applications of derivatives. And the first one we're going to look at is what is called related rates. Now, a rate, if you recall from elementary school or things you've seen in the past, it's how much something changes per unit time. So it's how much something is changing per unit time. So some examples of some rates might be miles per hour. So that is how many miles you travel in 1 hour. You could have dollars per second. How much do you make at your job every second? Probably not very much. So you can have all these different rates. So in a related rates problem, we have lots of equations that will relate one or more quantities. So there's lots of equations out there. So if you think about a volume equation, volume equals pi r squared h is the volume of a cylinder. It has lots of different variables. Well, we can figure out how much a volume is changing in relation to how much other things are changing. And these are what are called related rates. So related rates problems is how much one rate is happening, or one variable, not one rate. One variable is changing with respect to time. When another rate is changing. So it's how one rate is changing versus how another rate is changing. But we both do this with respect to time. Now, the process is not very hard to do a related rates problem. The hard thing is finding out what equation you use. And the calculus is not hard. It's really just setting up the equation. That's really the only thing hard about a related rates problem, because we want to see how one thing is changing versus another variable. Okay? So we're just going to look at some examples, and then we'll try lots of these. And we'll try a lot on our own. So here is the first example, and we'll kind of just go through the steps. So this says air is being pumped into a spherical balloon at a rate of 5 centimeters cubed per minute. So we have a spherical balloon, not a very good sphere. So I am pumping air into this balloon at 5 centimeters cubed per minute. So when I pump air into a balloon, the question is, what am I increasing? Well, if I increase the air in the balloon, what I'm doing is I am changing the volume. So what I'm given here is this is how much the volume is changing every minute. So in calculus terms, we say this is dV dt. Remember, the d means how much it's changing, so it's how much the volume is changing when the time changes. You're changing the volume by 5 cubic centimeters every minute. In our question in this one, we want to know how fast is the radius changing when the diameter of the balloon is 20. So obviously when we increase the volume of this radius is going to change, but it doesn't change at a steady pace. It will change, it will go up and down depending on how big the radius. Because when the balloon is really small, if you start putting air into it, the radius is going to increase pretty quickly. But when your balloon gets really big and you're putting the same amount of air in every minute, that radius is not going to increase as much. So what we're trying to figure out in this problem is what is dr dt? How fast is the radius changing with respect to time? So this is a very, very common setup where you have one rate you're given and you want to find another rate. That's why we call these related rates. And so we wanted to find dr dt when the diameter of the balloon is 20. Well, if diameter is 20, then the radius is obviously 10. Because remember, diameter is all the way across a sphere or a circle. So the radius is half of that. So we find out which rate we're given and which rate we want to find. Now what we have to do is we have to find an equation that will relate V and R. We want to find an equation that relates these two variables. They don't have to have time in it. They just have to have those two variables in it. And so a lot of times this will be geometric formulas. We'll do Pythagorean theorem, things like that. Not stuff you have to memorize as far as geometric formulas, but for a sphere, the volume of a sphere is 4/3 pi r cubed. That's a known formula. So if you ever want to find the volume of a sphere, it is 4/3 pi r cubed. So now we want to find dv dt and dr dt, but if you notice, there is no t in this problem at all. Oh, there's a v and there's an r, but there's no t. So what we're going to do is we are going to use implicit differentiation. And implicit differentiation is when you take the derivative of the variable, but if it's not t, you have to add the extra little dv dt or dr dt. So when we did this with implicit differentiation earlier in the semester, we would do it with a y. If we did anything derivative with a y, we'd add dy dt. Same kind of idea for this one. So if I take the derivative of v, the derivative of v is just 1, but it's not t, so I'm going to add a dv dt. And you can see why this is important, because we know what dv dt is. And then we have 4/3 pi, that's just a constant. Now I'm going to take the derivative of r cubed, which is going to be 3r squared, but I took the derivative of something that's not t, so we'll add a dr dt. And the whole benefit of this is, if you look now, well, this is what I want to know, and I have this, and I have r, I have all the other variables I need to plug in. So really I just have to simplify and plug some numbers in now. So like I said, the hardest part is getting that initial equation. So I know dv dt, I can cancel these 3's out, is going to equal 4 pi r squared dr dt. And since we're trying to find dr dt, I'm just going to divide the 4 pi r squared to both sides. So dr dt is going to equal dv dt. And since I'm dividing it on this other side, I'm just going to write it as 1/4 pi r squared. So we have the missing rate we want. We know dv dt. dv dt, remember, is 5. That's how much the volume is changing. And we know the radius. The radius is 10. So all we have to figure out is what this simplifies to. So if I simplify, it's 5/400 pi. And it's how fast the radius is changing. Well, the radius is in centimeters, so it's centimeters per minute, because the initial volume was centimeters cubed per minute, so our time is in minutes. So, and this is just a radius, so it's just linear. If I want to simplify it, I certainly can, because this is just going to be 1/80 pi, centimeters per minute. So when the radius is 10, that's how fast, when the radius is 10, that's how fast the radius is changing. Now, you can certainly figure out what 1/80 pi is, and I'm going to assume it is not very big. It is 0.00397 centimeters per minute. So if you think about this, when the balloon is already 10 centimeters wide, for a radius 20 centimeters all the way across, and you're only adding 5 cubic centimeters every minute, this is not going to increase how big the balloon is. It's not going to increase very fast. And the bigger your radius gets, the bigger this balloon gets, even slower it's going to grow. Now, if this was 1, let's say the radius was 1, then this would be growing much, much faster every minute. All right, so just a quick recap, because we'll do lots of these examples. So we figured out what rates we needed. We found an equation. We differentiated with respect to time. We solved for whichever rate we wanted, and then we just plugged some stuff in. So this is going to be a very, very reoccurring theme. We're going to find what rates we need, which ones we have. We'll find an equation that relates them. We'll do some calculus, and then we're just really going to plug in some numbers. Okay, let's look at another one. So this one says we have a 15-foot ladder resting against a wall. The bottom is initially 10 feet away from the wall and is being pushed towards the wall at a rate of 1/4 foot per second. How fast is the top of the ladder moving up the wall 12 seconds after we start pushing? Okay, so this one is a pretty common kind of problem. So let's go ahead and draw our situation. We have a 15-foot ladder. So this ladder is 15 feet long. Now, when we push this ladder from the bottom, we're going to push this ladder towards the wall. And we're pushing it towards the wall at 1/4 foot per second. And when you push it, the ladder is obviously not going to change lengths, but the top of the ladder is going to go up. The top of the ladder is going to go up the wall, okay? And initially, we know this ladder is 10 feet away from the wall. And the question is, how fast is the top of the ladder moving up the wall 12 seconds after we start pushing? So let's go ahead and just talk about what we have here. So essentially, we have a right triangle. This side is 15 feet. So this side I'm going to call X, and this side I'm going to call Y. Now, what we'd like to know is we'd like to know how fast is the top of the ladder changing. So really in this problem, what we want to know is how fast is Y changing. We want to know what is dy dt. We want to know how fast the top of the ladder is, how fast is the Y going up per unit time. Now we know a rate, we know 1/4 feet per second, but that's how fast the X is changing. So we know dx dt, that's 1/4 feet per second. So this is our initial problem. And what we want to know is we want to know how fast is it going up 12 seconds after we start pushing. Well, after 12 seconds, let's go ahead and draw it over here. After 12 seconds, this ladder is still 15 feet high, but this bottom is 7 feet now. Now, why is it 7 feet? Well, if we take 1/4 times 12 seconds, that is 3 feet. Okay, 3 feet, because it's getting smaller. So because we consider this getting smaller, it started at 10, it got 3 feet smaller, we're also going to make this rate negative. So I'm going to make the rate negative 1/4. Why negative 1/4? Because since we're pushing toward that wall, that distance is getting smaller. So it has to be negative. So we have, this is my initial condition. This is my initial triangle. This is what it looks like at this moment I want to figure out. So we have to figure out what is an equation that will relate these two variables. Well, this is a really nice one because it's a right triangle. And in a right triangle, we know we have Pythagorean theorem. So x squared plus y squared equals 15 squared. And so now we can differentiate with respect to time. So we have 2x dx dt, because again, we take the derivative with respect to t only, plus 2y dy dt equals 0. Now, we know, let's see what we know. We know dx dt. We know x. We know we want dy dt. This is what we want. So the only thing we really need to know is y. So we can find y because if you look over here at this right triangle, we know two sides of that right triangle. We know one side is 15 and one side is 7. So if I want to find the other side, I'll simply do 7 squared plus y squared equals 15 squared. That's going to help me find how far is the ladder up at this moment. So 7 squared is 49 plus y squared equals 225. 225 minus 49 is going to be 176. So y is going to equal square root 176. So that is going to be this other side. You certainly could figure it out in decimal form, but I'm just going to keep it in radical form. And so since we're trying to find dy dt, I'm just going to solve for it. So I will subtract 2x dx dt to the other side. So I'll get 2y dy dt equals negative 2x over dx dt. So I'm just subtracting this term to the other side. And so then dy dt, if I divide both sides by 2y, is going to be negative 2x divided by 2y times dx dt. So I'm just solving really for dy dt. And so now dy dt, which is what I'm trying to find, I have all the values in it. I have x, I have y, I have dx dt. So I'm really just going to start plugging things in. So if I plug it in this problem, dx or dy dt, I can cancel these 2's out, so that's always nice. So it'll be negative 7 over square root 176, because that's my x and my y from my initial problem, times dx dt, which is times negative 1/4. And that's going to be in feet per second. That's going to be what my rate is. So dy dt, the final answer, is going to be positive 7 over 4 radical 176, and that's going to be in feet per second. So again, not a very big one because the bottom is only changing at 1/4 feet per second, so not very fast. So it makes sense that this top one does not move very fast either. But there's a lot going on in these problems, right? We had to make an initial equation, we had to take the derivative, then we had to find all the values that go in there except for the one rate we want, because we're always trying to find one of those rates. All right, so let's look at this problem. This says, how fast does the water level change in a cylindrical container which is losing water at a rate of 3 liters per second? Now this one's kind of a more generic problem because it doesn't give us a lot of numbers. So we have a cylindrical container and it's losing water. So it's losing water out of the bottom, let's say. So the volume is changing, because when you lose water, the volume changes at 3 liters per second. So negative 3 liters per second, because we can think about it as losing. So this water is going down. And we want to know how fast does the water level change. So we're basically saying how fast does this water level change h? So our question is, how fast is h going down, dh dt? And we can ask, is it a constant rate? If the water's going out at a constant rate, does it go out at a constant rate or does it change? And so we'll have to figure that out. So if you know about the volume of a cylinder, it is pi r squared h. So we have 3 variables here. Now, in this case, I don't really have a way to get rid of r. I really like only if I have 2 variables. I'd love if I just had v and I had h, but I have this other variable of r, and I don't really see a good way to get rid of it. Now, the nice thing is that it's not going to matter in this problem. So if I differentiate dv dt, it's 1 times dv dt. And I'm going to just pretend that r is a constant, because r is not going to change. If I have this problem, this radius, as the water goes down, the radius doesn't change. The radius is going to always be the same for this whole cylinder. So I'm just going to pretend it's a constant. So pi r squared, that's fine. And then it's going to be 1 times dh dt. So our problem in this case, we know something for this. We don't know the radius, but the radius is just a constant. It's a number, so we don't have to worry about it. And then dh dt is what I'd really like to find. So I'm going to solve for that. So if I solve for it, I'm going to divide both sides by pi r squared. So dH dt is going to equal dV dt times 1 over pi r squared. Because I'm dividing it to both sides, so like I did earlier, I'm just going to do it by pi r squared. Now, I don't know what the radius is, but it's a constant, but I do know dV dt is -3. So our final answer is going to be -3 times pi over r squared, or -3 over pi r squared. And since the r is a constant, we'll just say it is that. And I don't really know what this is measured in. It could be centimeters, it could be whatever it is. So we'll just say units per second. So if the radius and height are measured in centimeters, it'd be centimeters per second. But in this case, we'll just say unit. So this is an example, and there's not a ton of them, but you will see sometimes where you have a related rates problem, where you have this third variable that doesn't change, and that is just kind of part of your solution. So once you know more about this cylinder, you could certainly find out how much the height changes. So if we did any cylinder problem, I could really just use this generic formula right here and just plug in R and then whatever dV dt is, and we know how fast that water level is going down. All right, let's look at our next one. The next one says 2 people are 50 feet apart. So I'm going to draw that first. So we got 2 people 50 feet apart. One of them starts walking north at a rate, so the angle between them changes at a rate of 0.01 radians per minute. So we'll say this guy starts walking. You know what? I'm going to make it south because I ran out of room. So we'll say he's walking south. It's the same problem. Doesn't matter. So he starts walking south at a rate, so the angle between them changes at a rate of 0.01 radians per minute. So if this person's up here now, and I take this kind of a segment, we have this angle formed between them. We'll call it theta. So this angle is changing. So the angle theta is changing at 0.01 radians per minute. And so the question is, at what rate is the distance between them changing when the angle between them is 0.05 radians? So the distance between them, we'll call it z. And so the question is, we want to know how fast is z changing? How fast is dz dt changing? And obviously, as you walk further away, you're going to get further and further away from this person. And we want to know how far away, how fast is it changing when the angle between them has a radian of 0.05. So that is our question. So we have a couple things here. Our initial condition, we'll always have an initial condition, right? This is kind of like the triangle we did before. We know the radian is going to be 0.05 radians. This will be still 50 feet, but we'll have to find out how far they are away. So the question is, can you find a relationship between theta and z in this triangle? And the answer is yes, of course. And in this case, when you have an angle, whenever you have a problem with an angle, you're typically going to do a trig relationship. So if I look at this initial one, this is my opposite side, this is my adjacent side, and this is my hypotenuse. Well, in this case, I know something about the adjacent side. I'd like to know something about the hypotenuse, and I know about the angle. I don't really know anything about the opposite side. But I have a trig relation that relates adjacent and hypotenuse. And if you remember SOHCAHTOA, that is cosine. So cosine theta is going to equal the adjacent over the hypotenuse. So in this case, that's always 50 over z. So this is the problem we have to deal with. Okay. So what we'll have to do is we'll have to now differentiate with respect to t. We'll also have to go over here and we'll have to find z. So since we're trying to find dz dt, I would actually do this a little different than other ones. So what I would do is I would actually solve this for z first. So I would multiply both sides by z, and then I know z is going to be equal 50 divided by cosine theta. And I can actually simplify that further because if you remember our identity, 1 over cosine is actually secant. And we like the derivative of secant is not bad, so I actually think it would be easier to do this problem this way. So z is going to equal 50 secant theta. Now, to find this value over here, if I want to find the z over here for our initial condition, we can certainly do that. It's going to be 50 over cosine of 0.05. Now, you can just put that in your calculator. Make sure you're in radians, because remember our angle's in radians. So you'd have to go to your mode and make sure your calculator is set to radians. On Desmos, it defaults to radians, so that's nothing you got to worry about too much. And that is going to be 50.06. So not much difference, right? So not much difference in this radian measure. And that's in feet. So let's come back over and do some calculus. So this will be dz dt, because the derivative of z is just 1, equals 50. Now, if you take the derivative of secant, that's one of those weird derivatives, but it is secant theta tangent theta d theta dt. And the nice thing is we want to know what dz dt is, so it's already by itself. So all I have to do is really plug in this radian measure, 0.05, and it looks like I didn't even need z. I found z at 50.06, but I didn't really need it because there's no z's left in the problem, because when I did the derivative of z, it just went away. So that's nice. So dz dt is going to equal 50. Now it says secant of theta, so secant of 0.05. Most of us do not have a secant button in our calculator, so we'll talk about how to deal with that. Times tangent of 0.05 times d theta dt, which is 0.01. So if you want to put it in your calculator, now Desmos has a secant button, so you can certainly do it, but if you're just using a calculator, you could just make secant, you could put it back to 1 over cosine. And then times 0.01. And that will tell us how fast this thing is changing. And it's going to be in feet per minute. So you just put all that in your calculator. So I tossed all this in my calculator, and I get 0.025 feet per minute. So they are not moving very quickly away from each other. But if you think about it, the angle is only moving 0.01 radians every minute. Now in degrees, since we're a little more familiar with degrees, that's like half a degree a minute. So if you can imagine yourself only turning half a degree a minute, well, you're not moving very fast, and the other person's not going to have, the distance between you is not going to change really quickly. So that actually makes a lot of sense. All right. So we are going to stop our notes here. These last two examples I want to do in class when we come back next week. So we'll stop here, and then we will, like I said, we'll come back and we'll do these next time.